In this video, we are going to derive a formula for the precession of pericenters in any theory of gravity which is described by the parameterized post-Newtonian formalism. This includes, as a particular case, general relativity. If you remember, we have already found a formula for the precession of the perihelion of Mercury for general relativity in one of the first videos of this lecture. However, here we are going to do it in a different way. You could do it in the same way, but we are going to profit from our study of the Kepler problem, of the classical Kepler problem, which is in the last few pages of the lecture notes, and which I encourage you to read right now before continuing watching this video. In that review, this precession is related to the variation with respect to time of the Laplace Runge length vector. And well, a formula is given there, and we are going to use that formula. I will explain a bit what is the logic again, but really you should read first those pages in which the Kepler problem is reviewed. Okay, first of all, we are going to use the formula that we derived in the previous video for the motion of a particle in the gravitational field of a point particle, in a spherically symmetric static gravitational field in this post-Newtonian limit. Remember that we wrote it in this way. Okay. Plus eta I. Here I am using kappa as GM, and in fact, okay, if you look into this review of the Kepler problem, this probably should be the total mass. Okay, the total mass is the sum of the two masses involved in the problem, capital M and small m, which should be the larger and the smaller. Eta I, we computed it for the particular case of this post-Newtonian or parameter post-Newtonian formalism. Okay, it is given there. I'm not going to copy it again, but we will use the explicit form later. If, well, as you have probably read by now in this review of the Kepler problem, apart from the conservation of momentum, linear momentum, and angular momentum, you can prove that in this problem there's a conservation of another vector, so another three quantities, and these three quantities are the Laplace are the components of the so-called Laplace Runge length vector. Okay, and the components of this vector are this one, so I, j, k, x dot j, l, k, I will explain what capital L is, minus a half of kappa mu x j over r. And here mu is the reduced mass, which is defined as the inverse is 1 over capital M plus 1 over small m. You know that the Kepler problem reduces effectively to that of a particle of mass mu moving in the field of created by something of total mass m plus m. Okay. Now this Li with, it doesn't matter if the indices are up or down. I am not distinguishing between upper and lower indices when I deal with three-dimensional Euclidean indices. Is the angular momentum of this effective particle, and as you know, is the vector product of the position vector and the velocity vector, and in components is just this. Okay, we express vector products with this epsilon. When eta I is 0, then this is really a conserved quantity. Conserved, according to the Noether theorem, means that this is proportional to the equations of motion of these variables xi times the variations of the xi that really give rise to this symmetry. In fact, there are 3 invariances or a vector of invariances, so this should be something like this, and this would be the 3 independent transformations, and probably there is a minus sign here, I think. Okay, so on shell, and if this is, let me put just k, referring to the classical Kepler problem. So when the equations of motion are those of the classical Kepler problem with eta equal to 0, this is 0 on shell. However, when the equations are different, okay, when they are satisfied, instead of this being equal to just this, okay, what you have is that this plus this is equal to eta, and then you can replace this by eta j, essentially. And if you know this, which is given in these notes at the end of the lecture notes, then you can write the expression for the variation of ai. The other thing that you need to know is that this ai is a vector that always points, when we are dealing with orbits, with Keplerian orbits, it always points towards the pericenter. So if you have an elliptic orbit, more or less, okay, this vector a points into this direction. Okay, this is not really, as you know, my drawings are not very good, so maybe if I exaggerate this a bit more, okay, something like this. The modulus can be different. It doesn't have to go right from the focus to the orbit. The really important thing is that it points towards the pericenter. Okay, so the next thing that you can do is, okay, if this is different from 0, this means that this pericenter is moving. Okay, which in practice means that, the orbits, okay, if this eta is really can be treated as a small perturbation, the orbits will be something like this, okay, and this vector will start pointing in slightly different directions, okay. And so what the shift of the pericenter is equal to the angular velocity of the vector. Now, a formula for this angular velocity is derived there, okay, and this phi 0 is really the angle that the vector A forms with some axis, okay, whatever, at the initial time. But this is not constant anymore. It was a constant. It was in fact a constant of motion of the exact Keplerian problem. Now it is not 0 anymore. And you can easily see that this derivative is nothing but the vector product, okay, of this times a dot, okay, where this Li is Li divided by mu, so the angular momentum per unit mass. Okay, then also in these few pages at the end of the lecture notes, there are lots of calculations involving to compute this, because the idea is that to first order you can compute this derivative by substituting the expression for A and so on for the Keplerian orbits. Okay, remember that the Keplerian orbits are given, can be written in this form. This is the best form to do it, to write them. Okay, and phi dot is just L divided by R squared. So this is now what you have to do is come here. This gives you a dot I, or this derivative, as a function of eta, and the rest is given by well, this expression R, because L is given by this, removing mu. So you know for the Keplerian orbits x dot, and so on. So it's a long calculation. Okay, and the only thing that you need to do is to be patient and replace the values of all these quantities. Okay, now if you are using the Keplerian orbits, but the information about the gravitational theory is contained in eta here. Eta will depend on gamma and beta, these post-Newtonian parameters. And okay, this is a long calculation. I am going to give you a reference in which this is computed. Okay, this is the paper by Young and Lin. Well, it is called Illustrating the Covariances of General Relativity by Perihelion Precession. This European Physics Journal Plus 129. This is the volume 2014 47. You have to look into section 3.3 and equations 31. Okay, basically they give you the result. The only problem with this method, which Weinberg says it is the most efficient, is that you get a lot of terms. Okay, so you get many terms. Some of them, Weinberg says that many of them vanish, but you first have to compute them. Okay, and then show that the integral vanishes. And so it is not that efficient. You get a lot of terms. So an efficient way to do it would be to put all the terms in Mathematica, and that could be it. This is what actually is done in this paper, and these people just do it in 3 different coordinate systems, and they get exactly the same result, which is what you expect. It is not a great paper. I just mention it because really it's more like an advanced exercise that you could perfectly do on your own. Okay, so this means that you are almost at the level of publishing this kind of papers. Okay, so how do you actually compute now the shift of the perihelion? You want to compute this. Okay, the formula is this gives you how it changes with time, but you want to compute how much it changes per revolution. In this approximation, a revolution would be when phi, this phi, not phi 0, goes from 0 to 2 pi, for instance. Okay, because this is for in this approximation in which we are using Keplerian orbits to compute this part of the formula, a full revolution is, from 0 to 2 pi. So delta phi 0 would be the integral between 0 and 2 pi of d phi 0 with respect to d phi. Okay, if you want d phi, to integrate this variation from 0 to 2 pi. Now, this, using the chain rule, would be this that we have, and dt d phi, which is just 1 over phi dot, which we also have because we know what r is. Okay, so you can replace this by r squared divided by L d phi, and r squared is p squared divided by L, and 1 divided by 1 plus e cos phi minus phi 0 squared d phi. Now this expression, okay, when you come here, will always be given as a function of phi as well. So here you have a bunch of sines and cosines, and you just have to integrate. And this is the part that Mathematica will do best for you, or if you, but then just because there are many terms, it's not that they are too complicated, but there are many. Okay, so when you do the calculation, and this is the formula that these people give you, you find that this is 2 pi k divided by p times 2 minus beta plus 2 gamma. Okay, and this is the formula. Remember that k or kappa, it's gm total. Okay, so this is the formula we were after, and this is a general formula for the precession of the perihelion per revolution in any of these theories, in the approximation in which the star, the planet, or whatever that produces the field can be treated as a point. Okay, and you just have to replace the values of beta and gamma. Remember that in general relativity, beta and gamma are equal to 1, so delta phi 0 is just 2 pi g and total divided by p, and 2 plus 2 minus 1, this is 3, so this is 6. Now you can compare this result with the one we obtained in a previous section. Okay. Now the idea is that instead of just comparing with this prediction of GR, you would compare the experimental results with this more general expression, and the experimental results will give you constraints on this combination of beta and gamma. Okay, just this measurement will not be enough to determine the values of beta and gamma. It gives you a combination, but of course now you can do more experiments, and the next experiments that we are going to consider are those involving the motion of light, or radio waves, or something like that, electromagnetic radiation, and we are going to do this in the next video.